All right, connecting the first and second derivatives. We'll take a look at the first derivative test for local extreme, that's review. We'll add on to that today points of inflection, which is where the second derivative is equal to 0, similar to critical points for first derivative. We'll take a look at concavity, which is the second derivative test for functions. And I do not give you the second derivative test or teach the second derivative for local extreme, because I think it's a lot easier to just simply use the first derivative, and we can get the extreme from first derivatives very easily. So we'll start by taking a look at our graph again. Here's our lovely graph, first derivative test for local extreme. We've already studied and looked at this idea. Remember that we're looking at the behavior of the function, keep this in mind today, when we're studying the derivatives. So derivatives tell us, first derivative tells us about where the function has a minimum, maximum, where it's increasing and decreasing, and where the function has a slope of 0 for min and max. Again, here's the graph we've already looked at. So we've already talked about this as well. You don't need to write all of this down necessarily, because we've discussed this. At a critical point is where the first derivative changes sign from positive to negative or negative to positive. If it doesn't change sign, then it has no local extreme value. So we talked about that idea that if you go from decrease to increase, it's a minimum. If I go from increasing to decreasing, it would be a maximum point on the graph. If it doesn't have that sign change, there's no local extreme. Remember that even though it's a critical point, remember a critical point can also be where the first derivative is undefined. We can add that when we start sign charts today to our discussion, but it still won't mean that there's a minimum or maximum necessarily at that point. So I want to start with just the first derivative and show you how to set up and use a sign chart today. Find the critical points for x cubed minus 12x minus 5. Find the local and absolute extreme values. F is given that it's continuous and differentiable. We'll start with the critical points. To find the critical points, we find the first derivative. And where the first derivative is equal to 0. Now, since it's telling us that f is continuous and differentiable, we don't necessarily have to worry as much about critical points where the first derivative is undefined. It's just a polynomial function. If you have a denominator or you have a function that you need to worry about that, you would check where the first derivative is 0 to get your critical points, and where the first derivative would be undefined, where you have a 0 in the denominator, for example, or where you simply don't have any points existing on the graph. Take the first derivative in this case, because it's just a polynomial, set it equal to 0 and solve it. 3x squared equals 12. X squared equals 4. What are my two values I get for x? We have two critical points. To write and identify the sign chart, and this is where I talked about it's going to be something that's going to be easier for you to read everything off of, just remember that after I teach you sign charts, you still on the AP questions that we read and practice in here, you still need to write out your answer when you're done. Sign charts are no longer just in and of themselves an acceptable solution. You have to still write some stuff. All right, so here's what I'm going to do. At the points where the derivative is equal to 0, I'm going to identify those points. How many sections I make and put on this particular sign chart is really just dependent upon how many critical values I get. So the size of the sign chart isn't going to be certain size for every problem. It's just according to the problem. So we have two different things to put in our sign chart. We have the sign of the derivative and the behavior of the function. Always remember that the derivatives are telling us about the behavior of the function. I'm going to then put some intervals in the sign chart. And the reason I'll put the intervals in the sign chart is then I'll be able to read all of my answers about where the function is increasing and decreasing at the values that I can tell where it changes from increase to decrease or decrease to increase, whether it's a minimum or maximum point, and I can identify all of those values. So I'm going to label the graph with the 2 critical points, or the chart, I should say. Then I'm going to put there's no endpoints here, so put the intervals here. This would be from 2 to infinity. This will be from negative to positive 2. And this would be from negative infinity to negative 2. Those are the intervals that separate negative 2 and 2. If I want to know whether or not the derivative is positive or negative, you don't necessarily have to graph it, or if you don't have a calculator to use for the problem, all you simply have to do is take a number and pick a number in this interval. So pick a number between negative infinity and negative 2. Halsey, pick a number between negative infinity and negative 2. Negative 6. So if I take negative 6 and plug it into the derivative, remember this is derivative, what do you get? A positive or negative number? That's all you need to know. You don't need to know exact number, just would the answer be positive or negative if you plugged in a negative 6? Positive. So I'm going to put a plus here for positive. Pick a number between negative 2 and positive 2. Sunny, pick a number. 0. 0 is very easy to work with. That's the common choice. If I plug in 0 for x into my derivative, would the answer be positive or negative? So for negative, I'll put a negative sign there, a negative symbol. And then from 2 to infinity, pick a number, Ellen, from 2 to infinity. 4. If I plug in 4, would the answer be positive or negative when I plug 4 into the first derivative equation, 3x squared minus 12? If the first derivative is positive, the function is increasing. If the first derivative is negative, we said that the function is decreasing. And here, if the first derivative is positive, the function is increasing. If the function goes from increase to decrease, that means that this would be a maximum. If the function goes from decreasing to increasing, it means that the function at this point would have a minimum. Now I can read all of the information from my sign chart that I would need to know from the first derivative, which is the function is increasing, then decreasing, then increasing. And if I have to give an interval where it's increasing and decreasing, that's simple as well. It's decreasing from negative 2 to 2. I read it from the top part of my sign chart. It's increasing from negative infinity to negative 2 and from 2 to infinity. And it has a maximum at negative 2 and a minimum of positive 2. Now I have all the information I need in one simple little chart. And I can read all the information from the chart. Questions? Let's try a little different problem. So I'm going to let you try this one, see if you can figure it out. All right, we have our first derivative using product rule. We factor out e to the x and we get this. How does this piece of it factor? Thank you. X plus 3, x minus 1. The big question is, where is e to the x equal to 0? Did you check it out? You can graph it and look at it. Where is e to the x equal to 0? If I put in a 1, e to the first is e, not 0. Right? So what value of x, in other words, gives me a 0? Can you find anything? You shouldn't be able to find anything because is e to the x ever hit 0? No. E to the x never equals 0. So this is something to remember and keep in your head because you're going to see this a lot on these kinds of problems. E to the x is never 0, so we don't even have to worry about that as a part of our critical point answers. It's never 0. I'll put that up here as a reminder for us. E to the x is never 0. So even when, no matter how many questions it looks really complex, just remember that. You never have to worry about that piece of it. So now I know the other critical points because if I take x plus 3 equal to 0, x would equal negative 3, x minus 1 equals 0, x equals positive 1. Now I have my critical points, negative 3, positive 1. Let's write our intervals, negative infinity to negative 3. If you have endpoints, you put the endpoint instead of the negative and positive infinity, by the way. Instead of that, you'd use the endpoint values. Negative 3 to 1 and 1 to infinity are my intervals. Pick a number between negative infinity and negative 3. Chris?
Negative 2, or negative 4.
Negative 4. So we put negative 4 into the first derivative, which is, we'll use the first derivative part up here. So it's a little easier to work with. All we need to know is if you put in a negative 4, would the answer be positive or negative? You can try it on a calculator. You don't have to try to do it all in your head if you don't want to. You can work it out on the calculator just to figure out, would it be positive or negative if you plug in a negative 4 into the derivative. Make sure you're plugging in the numbers in the derivative. So what is it? I heard someone say it. Positive, you're right. So that means that the function is doing what there? Increasing. So one of the things you could do is put a little arrow up. That also means increasing. Some people use all symbols on their sign charts, and that's fine, as long as you know how to interpret them. Pick a number between negative 3 and positive 1, Emily.
Negative 1.
Plug in negative 1 into the first derivative. Would our answer be positive or negative? What does that mean the function is doing? Increasing or decreasing? Good. Decreasing, and again, I can use a little arrow to signify that. Instead of write decrease, you can do it however you want. I usually write I and C and DEC for increase, decrease. You can use arrows if you really want. Pick a number that's bigger than 1, Caleb. 2. Plug 2 into the first derivative. Is the answer going to be positive or negative? Positive. Now, just in case you're wondering, because I know people ask this a lot, you do get a lot that vary, but you can also have it where they're all pluses. It's just a strictly increasing function, in other words. You could have them all minuses. You could have the first two positive and the third one negative. It just depends on the function. Okay, because I start doing some and then we get in our head, they always alternate. They don't. There's a lot of functions, as we know, that can be strictly increasing or decreasing. But then it'll tell us here, since the function on this one goes from increase to decrease, this would be a maximum. And then it goes from decrease to increasing, so that would make this a minimum. Now remember that these are where the derivative was equal to 0. If you have it where the derivative is undefined, what you do instead, I always do this just as my little side note to myself. Instead of writing the word max or min on the line, I'll put UND for undefined so that I don't forget that that's just undefined. It's a place where the graph has something going on and it's not defined at that point. And that just helps us to recognize that we're not going to call it something else. Here is the handout. People like this handout because this is when we start looking at the second derivative concavity, where people love the idea of what it looks like. So I'll talk about this for a moment. You can write stuff right on your handout if you'd like to. Concavity is the general shape of a graph, and when we look at second derivatives, it's exactly the same workings as first derivatives, and that will take the second derivative, find where it equals 0, and figure out where it's positive will be where the graph is concave up. Where the second derivative is negative is where the graph will be concave down. The hardest part for people is to understand the difference between concave up, increasing, versus concave up, decreasing. That's what the handout will help you with significantly. Again, people really like this handout because it shows it right on here. So this right here, everyone, is, think of an upward parabola. That's the way I always remember concave up, like an upward parabola. This one is concave up and increasing. This one is concave upward. Again, think of like an upward parabola, but it's decreasing. On the second one, these are both concave down. Think of, again, a concave down as like a concave downward parabola. This one is concave down and increasing. This one is concave down and decreasing. Again, this just really helps people get that perspective of what you're supposed to be sketching or drawing, if it's concave up and increasing versus concave up, decreasing, and so on. The rest of the things on here show us things like this, where the second derivative changes sign is where we're going to have an inflection point. So just like where the critical point, the first derivative, where you change sign, increasing to decreasing, decreasing, increasing, and so on, that's where the first derivative has a critical point. Its partner, as I call it, for the second derivative is called an inflection point. So let's take a look at that whole idea for second derivatives. The word is concavity. Concavity describes, again, the general shape of how the graph looks. So here's just another picture that shows us concave down, then the graph changes to concave up. So where the graph would change from concave down to concave up, we would have a point of inflection. And we solve it exactly the same way that we solve for first derivative tests. So concave up, the first derivative is increasing on that function. This is relating first derivative to second derivatives, really. Concave down, where the second derivative is negative, is where the first derivative is decreasing. That should make sense because where the first derivative is increasing is where you're going to have a positive slope. In other words, that's what it's saying. And where the first derivative is decreasing means that's where it has a negative slope. So that should make logical sense. And then here's the concavity test. This is relating it, everyone, to the second derivative. Where the second derivative is positive, it's concave up. Where the second derivative is negative, the function is concave down. Please remember, we're talking about the function's behavior and using derivative tests to analyze the function. We're going to put everything together here at the end of the notes and do a full problem, as I call it, which is increasing, decreasing, minimum, maximum, concave up, concave down, the whole kind of idea put together. Let's just start with real basic concavity, and then we'll do the big sign chart again at the end. But let's just start with basic concavity stuff. So can you tell me the concavity for a basic parabola, y equals x squared? Our restrictions are not existent, right? 'Cause it goes from negative to positive infinity. Always pay attention to this. Do you have a restriction? Are you graphing a piece of it or the whole thing? Huge difference, right? Because if I ask you the same question from 0 to infinity, it's a whole different answer. On this one, if we think about the derivatives, the first derivative is 2x. The second derivative is 2. Tell me about the number 2. Is it positive or negative? It's a simple question, right? Positive. So what this is saying is the second derivative is always 2, so it's always positive. The second derivative, always positive, means that the graph itself or function is going to be concave up. That should make sense because it's an upward parabola. I'm going to let you graph the second one from 0 to 2 pi only. Determine the concavity of 3 plus the sine of x, and then we'll see what you come up with. Here yet. All right, so the function is going to change concavity at pi, because that's where the second derivative is equal to 0. We need to write some intervals. We're going here from 0 then to pi. Actually, I'm going to use parentheses because that's more common, not to have the brackets on these. Which way is it? Concave up or concave down? Down. Graph the function. Again, take a look at it and see what's going on. So the other part of it goes concave upward. Again, think of downward versus upward parabolas. Sometimes you'll graph them, sometimes you'll figure them out algebraically or analytically, as they call it in the book. All right, here's probably the most important thing. Please write this down. A point where the graph of the function has a tangent line, and there's an and here, where the concavity changes is a point of inflection. So remember, critical point is where the first derivative is 0 or where the first derivative is undefined. That's an or in that one, okay, in that definition. This one has an and in its definition for point of inflection. So in other words, we have to check where it changes from concave up to concave down or concave down to concave up. And first thing I would check, though, is does it have a tangent line at that point? If there's no tangent line, if it's a piecewise function, if it has a discontinuity of some point, at that point, let's say at 2, you're looking at it and you solve it and you say, well, there's a point of inflection at 2. It changes concavity at 2. Well, what if it's a disconnect? What if you have a piecewise function, it goes concave down, and then you've got a little asymptote line at 2, let's say, or a point of discontinuity, and that goes concave up. There's no vertical, there's no tangent line, in other words, or no line here. You can't call it a point of inflection, so always keep that in your head first. Could I put a tangent line? So if it's just a nice parabola, let's say, or a nice function, so let's say we had a nice little function here, can I draw tangent lines at the points where it changes? So just think about, where can I draw tangent lines? This one you can draw them as many places as you want. So on this one here, this would be concave down and then concave up. And of course, it's continuous there. Now, it doesn't necessarily say it has to be continuous either, notice. It just says by definition where the graph has a tangent line and where concavity changes. We call it a point of inflection. So point of inflection goes with second derivative, first derivative goes with critical point. Don't get the two mixed up. here's what I was mentioning earlier. I do not teach second derivative for local extreme because I teach it with first derivative, but you can just take a look and see. It basically just says where the first derivative is 0 and second derivative is negative is a local maximum, which will make sense when you think about it. Where the first derivative is 0 and the second derivative is positive, you would have a local minimum. Where the second derivative is positive, think about you've got the concave upward idea, so it's going to have like an upward parabola, it's going to have a minimum. And the same thing here. This is like a downward parabola, so it's going to have a maximum. So it should make logical sense. All right, so let's do our ultimate problem, as I call it, and figure this all out. Let's find the first derivative is given. Oh, not the function, just the first derivative is given. We need to figure out about the function. F is continuous since f prime exists. The first derivative is 4x cubed minus 12x squared. Oh, so now we need to figure out everything we can about the behavior of the function. So here's our sign chart. We do the sign chart in 2 stacks. The first one is the first derivative stuff. The second one, of course, will be the second derivative work. So let's start with the first derivative. It's already given to us. All we have to do is figure out where this equals 0. What can I pull out of here? First, let's do some pulling out stuff. 4 and x squared. Okay, so we have x minus 3, 0. So 4x squared equals 0, x minus 3 equals 0. Where are my critical points? 0 and 3. Okay, what do we have here? 0 and 3 are the critical points. So let's write them down. 0, 3. Negative infinity to 0. 0 to 3. 3 to infinity. You see, everyone, by doing this, I don't have to go back and graph anything and look at anything to see the intervals. You're going to be asked, what intervals is the function increasing, decreasing? What are the local extrema, or the extrema in general, minimum, maximum, in other words? What are the critical points? All that we get right here from our sign charts. Pick a number between negative infinity and 0. Tess. Negative 1. Plug it into the derivative. It's right here. Remember, plug it into the derivative here. We talk about the behavior of the function down here. Positive or negative when you plug in a negative 1? Negative, okay. So that means the function would be what? Decreasing. Pick a number between 0 and 3. Andrea. 2. Plug 2 into the derivative. Would the derivative be positive or negative? Negative? Okay. And then pick a number from 3 to infinity. Caitlin. 4. Plug 4 into the derivative. Would it be positive or negative when you plug in 4? Do the same for the second derivative. So now I'm going to put the second derivative, I'm just going to write it over here on the left, the second derivative in this box, just because it's more, I'm going to run out of room otherwise. So let's find the second derivative. So derivative of 4x to the third would be 12x to the second minus 24x. Let's take and factor out a 12x. we're left with x minus 2. What are my values where the second derivative equals 0? 2 and 0. So 12x equals 0 means x equals 0, x equals 2. So 0 and 2. Here's the interesting thing. It's okay to have the same values. Notice the critical points. Critical just means an important point. We said that already on a graph. And notice on here, by the way, that it goes decreasing, decreasing. We'll talk about this here in a sec. We'll come back and look at that. And then goes to increasing. So what's going on at 0 is it's not a minimum or maximum, right? Here it goes and decrease, increase. This will be a minimum. I guess I'll write it on here. But then we'll talk about that when we get through this. So we have 0 and 2. So negative infinity to 0, 0 to 2, 2 to infinity. We do the same exact thing for the sign of the second derivative. So you plug the numbers into that you pick in each region into the second derivative. And then we talk about the behavior of the function. This is all about the function in the bottom part of our sign charts. So if we take a look at, here's our second derivative. We'll look at this. Pick a number between negative infinity and 0. Nick? Negative 1. If you plug a negative 1 into the second derivative, would it be positive or negative? Now here, our behavior is concavity, so it will be concave up. Pick a number between 0 and 2. Halsey? 1. So would the answer be positive or negative if you plug in a 1? Negative means that the second derivative negative means that the function is concave down. And then, Sunny, pick a number between 2 to infinity. 3. If you plug a 3 into the second derivative, what do you get? Positive or negative? Positive. Okay. So that would be concave up. So now in this one, it's just a polynomial function, so we know that it's going to have tangent lines. That's the big question first to ask yourself. Where it's not, again, is where you're going to have things like piecewise functions, asymptotes, things like that. So this one's okay that way, but look at 0. Tell me what's going on at 0. Bless you. Tell me what's going on at 0. Changes from concave up to concave down. So what is 0? Point of inflection. And then it changes from concave down to concave up, so it is a point of inflection. Now notice, at 0, it wasn't a minimum or maximum, but it's still an important point on the graph because down here at the second derivative, it changes to be, or it becomes a point of inflection. So it is an important point, but it didn't show up in the minimum maximum because it's a point of inflection. It's an important point, and it's where it changes concavity at 0. So that happens. You'll see at 0. You see that a lot at 0. It may not come up to be min or max, but typically it's going to come up to be still an important point on the graph. It'll show up as a point of inflection. So now if you're asked anything to describe the graph and analyze the function, we don't know the function. I didn't give you a point on the graph, so we don't know what the function is. We just knew the first and second derivatives. You could sketch the function for me by interpreting this. Where does it increase? Where does it decrease? Where does it have a minimum value? And you could sketch, I think everyone in here could sketch a fairly nice, just a sketch, a graph of what this might look like just by using the information from the sign charts.